So good morning. My presentation, as explained before, is focusing on illustrating to you the main achievements that have been reached within the other component of GEM. And I'm actually giving this presentation on behalf of a large group of people. So past and present members of the other team, PhD students working with us, scientists working at the testing evaluation facility, all the scientists that work within the regional programs, and the large group of people that contributed to the global components. Unfortunately, I'm giving this presentation on behalf of them, and I chose the worst presenter that is available, but that's unfortunate for you. Okay, so in order to illustrate the main results that we obtained within the other component, I thought that the best way to do that is basically to guide you through a very high level, path in the way that we perform an hazard analysis and how we can do that, explain you how we can do that using the products and the tools that GEM created. So when we want to perform an hazard analysis, of course, the first thing that we want to, understand if it's necessary to create a new model or to choose a new one. So if I have to generate a new model, clearly the first thing that I need to search for is for primary information. And in order to support these aspects, GEM, during the first implementation phase, sponsored 5 big global projects that generated data sets and guidelines, helping the modelers in the collection of basic information and guiding the modeler in the creation of components of another model. So we had 5 global components that created a global uniform instrumental catalog, one that created a global uniform historical earthquake catalog, one that created a global strain rate model, one that created a global uniform data set of active faults, and one that provided guidance on how to select ground motion prediction equations to be used for hazard analysis. All the results of these global components are now available on the GEM platform, and so the user can interactively understand the information that is available and eventually download this information and use it locally. There are also a lot of data sets that have been created actually within the regional programs that GEM promoted during the first implementation phase. Here I'm just showing to you an example of the database of active faults that have been created within SHARE. But there are many more coming from also other regional programs, such as the earthquake model for the Middle East and the model in Central Asia, coordinated by GES. So once I have the primary information, the next step, if I want to create a model, clearly is to process this information and to go from the basic data sets to the information that is used inside the engine in order to calculate the hazard. So in order to support this step of the hazard analysis process, we created 2 sets of toolkits that are helping a user to process the information and to create the source model and the ground motion model, which are the 2 main components of a hazard model. So for the creation of the source model, we created the so-called hazard modeler toolkit. The hazard modeler toolkit is basically supporting 3 processing workflows that are starting from basic information, seismicity, information coming from geology, and strain information. And from these data sets, going to until the creation of the source model. The second toolkit that we created, which is also something quite unique, is called the OpenQuake ground motion toolkit. The ground motion toolkit is helping the user in understanding the ground motion prediction equations that are available inside the OpenQuake engine, and is also providing tools in order to select the ground motion prediction equations that, based on information that is recorded locally, the best ground motion prediction equations to be used to a specific hazard analysis for a given region. The second option is instead to start from an available model. And in order to support this workflow, what we did is to collect models coming from the community, and what we did is to build a database of seismic hazard models. So all these models are now available on the OpenQuake platform, and I encourage you to come to the booth and see and interactively how you can inspect the models that are available. So what you can do basically is to enter into the platform, open a menu, and choose from a list one of the models. And once you choose a model, through the platform you can get additional information that is describing the main characteristics of this model. You can also inspect results that are pre-computed using the OpenQuake engine. And these results include hazard maps, hazard curves, uniform hazard spectra, but also the sources that have been used to calculate the hazard in that specific region. This is the current database of models that we've been able to create within the first implementation phase. We have 12 models that are all harmonized to be used for the OpenQuake engine. We have 2 models from the regions that will be available probably early, so in the first semester of this year. And we have also new models that will come by the end, most probably of this year, such as the new hazard model for the United States and the one for Japan, the model for New Zealand, published in 2012, the model that will be created within the regional program currently going on in South America, and the model for the eastern part of sub-Saharan Africa that is also currently in progress. So now we have a model built by us or taken from the platform. We want to perform a calculation. And in order to perform a calculation, what we did is to create the hazard component of the OpenQuake engine. So the hazard component of the OpenQuake engine, I think that now can be considered a tool that is well recognized within the international community and with very well identified features. So the main ones that I think are let's say, shared by all the community is that it's open, transparent, and accessible. It's well documented. It's extensively tested at the point that we created a specific report that is just describing all the testing methods that we are actually applying in order to make sure that we are providing reliable results. It offers different ways to calculate the hazard. And this is a very technical feature. Logic trees are an integral part of the input model, and that means basically reproducibility of the results. Some examples of application. So the hazard component of the OpenQuake engine has been used by all the regional programs that have been active during the first implementation phase. So SHARE for Europe, MF for the Middle East, MCA for Central Asia. Also for the project that has been going on in the Balkans. And it has been the engine used for 4 national seismic hazard maps already. So for Taiwan, Ecuador, Switzerland, and Turkey, used recently the engine in order to calculate their reference national hazard maps. The OpenQuake engine can be used as I explained, for regional models, for national models, but is also capable to perform very complex site-specific hazard analysis. In 2012, we have been enrolled in a project that aimed at the verification of the calculations done for a nuclear site in South Africa. Right? And this project actually proved the capability of the engine to provide results that are in very close agreement with software that is considered a kind of standard within this sector. Now we are also involved in a new project that is promoted by the Pacific Earthquake Engineering Research Center, and this project is about the verification of PSHA codes. And the OpenQuake engine is used by the Pacific Earthquake Engineering Research Center as a benchmark code within this exercise, which is something very, very interesting for us and very promising, given that our results are always matching very well against the results provided by the large set of software considered. Last point that I want to emphasize regarding the engine is that the hazard component is very well integrated with the risk component. And this will be more extensively explained later on by Vitor when he will discuss the risk component of the OpenQuake engine. Of course, everything we did in order to build the tools, the engine, the models that are part of the platform has not been done in isolation, and we actually invested quite a lot of time going around the world, explaining what we have been doing, and trying to get feedback from the community. So here you can see only a few places where we have been, where we had meetings with the local communities, where we had offered trainings of the OpenQuake engine and the tools that we are producing. And these are, as I explained before, the two regional programs that are currently going on and where we are investing a lot of time to work together with the local communities. The last point that I want to emphasize regarding the results that have been achieved is actually the work that has been done by the testing evaluation facility at Kerstedt in Posen. So having a model is not enough. It's very important to understand how the model behaves against the information that is eventually available. And in that respect, the work that the scientists working at the Research Center in Potsdam is very important, because they tested different aspects of they developed methods to test different components of another model. This is not work that so far has been integrated in our process, or I mean mostly the work that has been done by the GEM hazard team, but this is certainly something that will be very useful for the future. So what's next? What we are, let's say, planning to have soon in the future, where we are planning to go. So certainly we want to expand the set of collaborations we have within the region, because this is really very important for us. This is where there is value in the work that we do. We want, of course, to expand the database of models, and hopefully this is something that will be much easier in the future, because the use of the OpenQuake engine is increasing, and so soon there will be many models already available in the OpenQuake engine format. We want to add, of course, new features inside the OpenQuake engine, because we did a lot, but certainly there are many other things that it would be interesting and useful to offer to the community and to develop together with the community. And we want to continue improving the tools, mostly by answering the requests that are coming from the scientists working in the region. And for example, the work that we've been doing in Sarah was very useful and interesting for us in that perspective. So this was my last slide, and the really last one is about thanking you and everyone so during this first implementation phase had been supporting us. Thank you.
You know, we can say all we want about the utility and abilities of the OpenQuake hazard engine, but in the end, it's the community that decides. And what's happened is that countries are voting with their feet. So Switzerland, Ecuador, Taiwan are using OpenQuake for their next national hazard model. Canada and Australia are about to use it, and we believe many other countries will follow. This is really the sign that this tool has become a standard, and it's our dream that if this happens, people can intercompare their results. Australia and Canada both have large areas with very infrequent but damaging earthquakes. What assumptions do we make about them? In fact, they're done very differently in both countries. If we're using the same tool, if we're talking the same language, suddenly we can begin to understand our individual programs and put them together.